We are students of Delhi Technological University and we here present to you our submission for Texas Instrument Indian Analog Design Contest 2014. The title of our project is Parallel Processing Using Microcontrollers. The inspiration of our project lies from the fact that complex algorithms can't be performed over general purpose hardware but require special hardware like DSPs which require very high cost. Thus, we aim to utilize the power and capabilities of parallel processing to extend the execution capabilities of general purpose hardware such that complex algorithms can be performed over them. Thus, the idea of our project is to make a cheap, effective, and efficient approach such that the execution of normal hardware can be increased, keeping the cost very low.
The first step of our project is burning the EEPROM from where the opcodes will be fetched by the microcontrollers. Our EEPROM is 28C64A, which is an 8 kilobyte ROM. As you can see in the block diagram, first we make an assembly level program that has to be executed parallelly. Now rather than using an external EEPROM burner which is highly costly, we have burned the EEPROM using a microcontroller by putting address and data on parallel bus of external ROM, thereby reducing the overall cost of the system. The steps are performed as shown in the block diagram. The EEPROM requires some time to be written, so appropriate delays have to be inserted into the code. After 4 to 5 seconds, the EEPROM is fully programmed to be used. The next step of the project is to fetch opcodes from the external EEPROM. First, here in the diagram, we have shown interfacing the 28C64 EEPROM chip with our microcontroller, that is AT89S52. The microcontroller is based on 6 architecture and has multiplex address and data lines which are given outside for external use. In the system, first we execute the on-chip code from where the microcontroller gets the startup information and then makes a long jump to off-chip ROM from where it gets start executing the program code. Then the output of this program is read by Texas Instrument MSP430G2553, which is then displayed over a virtual COM port monitor. Now we move on to our proposed multiprocessor environment, which can execute the code parallelly and thereby increase the efficiency in execution. As you can see in the block diagram, by just adding a bunch of wires, we can extend the system to a multiprocessor one. The only adjustment that have to meet are that the opcode from EEPROM that was going only to the master now is given to the slave 2, and the transmitter pin of the slave is then joined to receiver pin of the master. So just by adding these two things, the code residing in the external EEPROM can now be executed parallelly. The components that we have used in this project are MSP430 development board, EEPROM chip AT28C64A, Atmel AT89S52 development board, Texas Instrument LM2930T50, which is a 5 volt regulator, Texas Instrument LM2937ET3.3, which is a 3.3 voltage regulator, Texas Instrument SN74LS373, which is a 8-bit latch.
Now we move on to the hardware implementation of our project. The hardware prototype has been shown here in which various components are used. First, this is the EEPROM chip which holds the opcode for the program that is to be executed. This is an 8 kilobyte ROM, that is 28C64A. The opcodes fetched from the EEPROM are taken by microcontroller AT89S52 which executes the code. The microcontroller has multiplexed data and address lines which are provided in port 0 and port 2. To demultiplex the address and data provided by the microcontroller, we have to use the Texas Instrument IC, that is SN74 LS373, which demultiplexes the address and data through the address latch enable pin of the microcontroller. After the opcode is fetched by the EEPROM, then the microcontroller executes it and the data output is read by the MSP430, which is then displayed over the virtual compute monitor. Further, two regulators, that is 5.0 regulator and 3.3 voltage regulator, are used for power of different parts of the system. Now we power up the system to show you first a single processor environment where only the master takes opcode from the EEPROM and executes it. As you can see here, the system is powered up. Now coming to the output, now here is a program that we have executed into the EEPROM. Now the output is shown here over the virtual compute, where we have calculated a 2-pin histogram for which the output is as below. Further, the execution cycles taken for the program are 420 here in the single processor environment. Now we move on to the hardware implementation of our proposed system, where we will see in the process that by adding just a bunch of wires, we can extend a single processor environment to a multiprocessor one. Here, this is the master and this is the slave. Now we will see that the output that was going only to the master is now given to the slave too. Further, we connect the transmitter pin of the slave to the receiver pin of the master such that they can communicate properly. Now again we power up the system. Now as you can see, both the master and slave are working and powered on. Now coming to the output of the system, here this is the part of code where master will communicate to the slave to get the data produced by the slave, and then does the final processing over the data. Here is the output that is again shown on the virtual compute monitor with the help of MSP430. Again we can see the output is the same as produced the single processor environment, but the execution cycles taken are reduced from 420 to 310, thereby improving our system by 110 execution cycles. Thus, from our project, we present to you an idea for external CPUs. Just like we have external hard disk today, we may have external CPUs which may be plugged into any existing device, thereby increasing its computational capabilities. Further, as shown in the implementation of our project, now two discrete units may be interfaced very easily without increasing much of overhead communication and overhead hardware.